Welcome back. I have one quick announcement. Tomorrow is the last day for exam registration. So I hope you've all done it, but if you haven't registered for the exam, do it today or at the very latest tomorrow. On Thursday, we had an exercise where we did a first version of a kinematics framework, where basically we were able to provide our code with a set of joint angles, and then we called recursive forward kinematics for the root of our kinematic tree, ran an outward pass, and it updated all positions and orientations within that tree. Over the course of the next exercise, we will extend that a little bit. Make it a bit more general, because so far we've only done two types of joints. We have only computed positions, but on the theory side, we have already developed all the tools that we can not only compute positions and orientations in this recursive manner, but also velocities and accelerations. And what is most important, we can do so in a structured way. So every velocity in our system, and especially every acceleration in our system, this is what we will need today, can be written as the Jacobian, which we can compute recursively, times q double dot, the accelerations of our generalized coordinates, plus some bias acceleration, which potentially depends on t, and then if we have non-holonomic constraints, we may have a different variable for velocities altogether. But overall, we have the structure, and we will heavily rely on the structure once we start doing dynamics. The reason for that is simple, right? In the structure, we can see that our Cartesian accelerations, and Cartesian accelerations, this is where the physics live, are linear in terms of the generalized accelerations. This is where we would like to describe things, because I don't want to think about, if I think about a multi-body system, sort of about the physical accelerations in 3D space. I just want to reason about what are my joints doing. And this is where we want to go to today. I want to start this next chapter with a quick recap of what the Jacobian is doing, because it will become very, very important in the following. And I want to do this along this problem 21, which was homework until last Thursday, which you then basically extended into an N robot. But the part that I want to talk about today is these two simple cases in problem 21, where I ask you to write an expression for the position and orientation of the end effector and these intermediate points, where I call them here points, but the information, the Cartesian information, is always three-dimensional: x and y position and a rotation angle. And then if we reason about velocities, accelerations, of course these are linear velocities and a angular velocity. And then you were also asked to write the Jacobians, which I have copied here from MATLAB into our notes. JA would be Jacobian for this example. JB would be the Jacobian for this example over here. And maybe the first thing that is important about Jacobians is the question of what's the best way of reading them, right? Mathematically, they're partial derivatives of our positions if we live in an inertial frame of reference, so if we don't have to account for any motion coming from the coordinate system. We thought about them as sort of the motion space, and we thought of them as lever arms. And one way to think about them whenever you see a Jacobian is to basically reason about what that Jacobian is doing. And in some very abstract sense, my Jacobian is taking a velocity in our generalized coordinates, so joint velocities, and produces a vector of Cartesian velocities. And these Cartesian velocities in case A, I can see, right, I have 6 rows here. So I have 6 Cartesian velocities, which I can directly separate into the 3 Cartesian velocities for my first point, P1, right? And so the rows would correspond to x, y, and gamma, xy position and orientation of body 1, and then the next 3 rows would correspond, not PE, but P2, but PE, the position of the end effector, which again has an xy position and an orientation gamma. So whenever I see a Jacobian, I can decompose it in individual lines, and each line would correspond to 1 Cartesian coordinates. I could also decompose them in other ways, where I say I'm only interested in the motion of P1, in which case I would only look at the top part of the Jacobian, or I'm only interested in the motion of the end effector, in which case I would extract the lower 3 rows. And in a very general way, you can do this with any Jacobian, that you can just pick individual columns and say, oh, that's sort of the sub-Jacobian for particular coordinates, or a set of individual columns and say, this is the sub-Jacobian for a particular body. Or I could just stack them on top of each other, give them another name, and say this is a combined Jacobian that gives me the information of all the bodies in our system, right? And of course, that works equally well in example B, where we have here the information for 3 bodies. So the first 3 rows would be P1, then we had P2, and then it would be PE, the end effector, on that example on the right. So those are the rows. In terms of columns, we also see such a subdivision where basically every column corresponds to an individual joint. So for the first example, this would be the column corresponding to Q1. This would be the column corresponding to Q2, written here, of course, as velocities, because that's what I will use the Jacobian for. So in terms of these x coordinates, Cartesian coordinates, I should also add dots, right? We're talking here about velocities. And then I do the same for the second example. A way to read this now is to think about your Q providing a unit rotation or unit motion about 1 generalized coordinate, which we set to 1, and all the other generalized velocities we set to 0. So my Q could be, for example, 1, 0 or 0, 1, 0, 0, which means I'm looking at the motion of one particular joint. Physically, I lock all the other joints in place, move that one joint with unit velocity, and then check what my Cartesian velocities are doing. So for example, in this example, if I set Q1 dot to 1, Q2 dot to 0, it means joint Q1 is moving with unit velocity, joint Q2 is locked, and I could basically immediately see that this would mean that my point P1 has to move in the direction of this Q1 motion primitive, and joint Q2, body PE, also has to move in the exact same direction, right? This is given through this column of the Jacobian, because joint Q2 would be locked, and I'm moving the entire assembly up and down along joint Q1. And this is what we see here, right? These are the directions of motion: no motion in X of P1, unit motion in Y of P1, no rotation of P1, and exactly the same for PE. Moving parallel, because that joint would be assumed to be blocked. If I now assume a unit rotation about joint Q2 and set Q1 to 0, this joint here would be blocked. That joint would be moving with a unit rotational velocity of 1 radian per second, for example, if these are our units. And what I would get is that this end effector is somehow moving in this direction, right, orthogonal to the lever arm from my joint center to the point that I'm looking at. And this would be indeed the direction that I see down here. So minus 0.1 in the x direction plus 0.1 in the y direction. By the way, these are not drawn to scale. I should make that very clear. Arrow length not to scale. We looked at this in more detail at some point. I don't want to go back into that, but the actual values that we see here would be the distance from here to sort of a vertical line and from here to a horizontal line going through this point, PE, right? So far, I think so good. There's one interesting thing that we see. We have a bunch of zeros here. What does that mean? In a very general sense, why does there have to be a bunch of zeros?
A change in Q2 doesn't affect our point 1.
And why is that?
Because it rotates around the point but doesn't move the point in any direction.
Okay. Does someone have another reason? Maybe going in the same direction.
Maybe because of the tree structure.
Mm-hmm.
The joints that are after the body don't influence the body before.
Yeah, so if we have to define after as being further away from the root. So a point that is closer to the root is not going to be influenced by any joint that is further away from the root. And in the Jacobian, this is reflected sort of by this lower triangular structure, which we see here with sort of just one zero element, but we see it much clearer down here, right? This body P1 is only influenced by the motion of joint Q1 because, sorry, I'm looking now at example B, because 2, 3, and 4, those joints are after P1. P2 is influenced by 1, 2, and 3, but not influenced by 4 because 4 is after P2, resulting in the 0 here. And then my joint, my end effector is affected by all 4 joints. And again, I could go ahead and draw all these directions of motion into our drawing. So for joint Q1, the motion that is creating is in this direction. And that motion is applied to every individual of these 3 points. Because again, we think if I'm moving about Q1 and blocking all the other joints, this entire robot is just moving up and down. If I look at joint 2, I would get very similar to the example on the left. I would get a rotation of P2 around the joint Q2. This arrow should be a little bit longer. At least I should try to make them halfway realistic, right? So this angle, this arrow is a little bit longer, but I'm rotating about Q2. P2 is moving in this direction. Where's PE moving to? As a consequence of a motion in joint 2. Right? What direction should I draw the arrow at this end effector PE? Andy, right?
Yes. Orthogonal to the vector between P1 and PE.
That's very important, right? So I have to basically look at this lever arm between the joint. We're talking about joint 2, right? So that's sitting in P1. And the point I'm trying to get the Cartesian motion, and then orthogonal to that, and the arrow should be a little bit longer than the arrow below because we have a longer lever arm. And again, this would be reflected, these distances, right? The distance from here to here, that's the lever arm in y direction, and you see that this is the same for P2 and PE. And the distance from here to here, or from here to here respectively, would be the lever arm in x direction, or the lever arm, distance in y direction gives me then a velocity in x direction, and that is shorter for PE and longer for P2, which we also see here, right? That point is higher up. So ultimately, if I rotate about Q2, since both points have the same horizontal distance here, their vertical velocity is going to be the same, but the horizontal velocity of this guy is going to be larger than of this guy because measured vertically, it is further away from the center of rotation. What about this one? So joint Q3, how should I draw that?
In the same direction as Q3, like in the same direction of P1 to P.
Mm-hmm. And again, sort of with the same length, right? These arrows that corresponds to translational motion, they should have a length of 1, right? Because there's not really a lever arm involved or a transmission ratio, right? The transmission ratio is 1. So they should have length 1. That's not drawn to scale here, because otherwise all the other arrows would be way too small. And now the idea is Q3 is moving, so the upper part of the robot is moving to the top right, and all the other joints are blocked. So of course these 2 points are moving with the same velocity in the same direction, and P1 is not moving, right? Because Q3 is after P1, which is what we see up here. And we see this also numerically. Here we have basically square root 2, 1 over square root 2 as our 2 directions, right? So this is a vector of unit length pointing in the 45-degree angle. The same here. And then we can do this one last time for joint Q4, where we see immediately, since this joint is sitting here, it's never going to influence P1. It's not going to influence P2. It's introducing a rotation about this point, which means that for this end effector up here, we get some motion purely horizontally. And that's also what we see here, right? We have sort of this component in x direction. No matter what the velocity, PE is not going to move in the y direction. That's why I have a 0 here, right? Because that arrow is pointing straight to the left. And then also note that all the rotational joints have a 1 here, right? Because any rotation about a joint is going to give me a rotation of the actual body reflected here by A1. You're all good with this? Yeah? Any questions? Then let me ask you one question about the number of degrees of freedom. How many degrees of freedom does my end effector have in case A? So degrees of freedom means independent directions in which it can move.
Yeah, I would say 2.
You would say 2? How would you argue that?
Because I have one translational option at quantum and one rotational degree of freedom at P1.
Okay, right, so this is just a counting argument. What we could do also is we look at these 2 arrows, right? These are the directions in which PE can move. And we nicely see they span a 2-dimensional space. We could also look at the Jacobian of this body P2, right? So we would, PE in case B, PE. As it's called here, we would have to look at this bottom Jacobian, and we would see there's 2 vectors spanning that motion space. They are linearly independent, so the rank of that Jacobian would be 2. Right? And it cannot be larger because it only has 2 columns. Right? So there's no way we're going to get more than 2 directions of motion. Can you imagine that we get less? Despite the fact that we have 2 joints, right? Could we get fewer than 2 degrees of freedom? So, Raphael, what do you think?
Yes, if we, for example, have
two translational joins in row or something like that?
Okay, so I'm not talking about a different system. I'm actually talking about exactly the system. So the question is there a configuration? Maybe Robert.
If Q2 is 90 degrees, both will move in the same path.
So thank you that you said that. I'm pretty sure that's what you wanted to say as well. It's not fully correct, but let's go with your argument for 1 second, right? If you imagine I set Q2 to 90 degrees, then the blue arrow would point straight up in the same direction as the red arrow. And in terms of translations, we would only get 1 degree of freedom, right? In that configuration, I would not be able to move this end effector left or right. So in a sense, you're right, but if I look over here, I realize that we actually think about the end effector as a 3-dimensional object or something that can move in 3 dimensions because it can also rotate. And setting Q2 to 90 degrees would make this column 0, would set this column to whatever D is. I have no idea. I think 0.15. So this is set to 0.15, right? I would have 0.15, 1. So the first 2 columns would be linearly dependent, referring exactly to the fact that the 2 arrows overlap. And I only in the XY motion, I'm left with 1 direction only. But then, of course, I also have the rotation. And in this world of rotations, Q1 and Q2 would be doing very different things. Right? So the idea of these singularities is you somehow align your joints that 2 joints do the same thing. Right? And in terms of x and y, if we align them as Robert suggested, they would do the same thing. Right? A motion in Q1 would move the end effector straight up. And if this joint is pointing, or this link is pointing straight to the right, a rotation about Q2 would move the end effector also straight up and down. Right? So in terms of these positions, x, y positions, they would do the same. But of course, Q1 is not going to rotate. Q2 is going to rotate. So mathematically, the rank would still be 2 of that Jacobian of PE. OK? What about the end effector in the second case? How many degrees of freedom does the end effector have over here? Tom?
3.
OK. We can look at the arrows. There's 4 of them. So it has to be at least 2, right? You can't really say anything about rotations by just looking at the arrows. But we shouldn't say it's 4-dimensional because there's 4 arrows, because obviously now we have some directions that are dependent. So what we should do is look down at the actual matrix, and we see that I have 1s and 0s in the 3rd row, so I clearly can independently actuate the rotation. And I have elements in each row, so this has a rank of 3. Right? It's now a 3x4 matrix, has maximum rank of 3. Same question. Can we find a singularity for this? Right? Can we find a situation, a configuration of the joints where I get a loss of rank? And if we don't want to do it for PE, right, we could also think about this point P2 here, right? Because if I look at P2, I see I can move it in y direction, I can rotate it, and I obviously can move it here in the x direction. So maybe that's easier. Forget the rest of the robot, just look at this point P2, or the segment described by this point P2. Can I get that into a singularity? What do you think?
If you choose
be 0, then Q1 and Q3 do the same thing. I think you would get a rankless in the Jacobian also.
All right, let's maybe do a quick drawing. So, sorry. Your suggestion is setting Q2 to 0, which then means that Q1, this motion, and that motion is doing the same thing. However, you still have Q2, right? So these two joints would give you a motion in this direction. Your Q2 would give you a motion in this direction. And then because, let me think about this, can I independently control the rotation? That's now the important question. And the answer is then probably no. Right, so what will we get here? For Q2, we would get a value here and a value down here. And this joint here, Q3, would be pointing purely in the y direction. It would be 0 and 1, right? So basically that entry and that entry would be exactly the same. And then this one would only combine motion in x with rotation. So we would end up with only 2 degrees of freedom, right? And the important thing here is in that the motion in x and the rotation are coupled, which is different to what we had on sort of on the other side, right? So in this case, we would have a clear singularity for P2. Right? And then with PE, we can never get that because we would have this joint Q4, which would then always allow us to independently do the rotation. You look puzzled? They're not explained as well, or do you disagree with what Mo is claiming? So thank you for that point, right? So again, same idea. Here would be my end effector, right? And now I would have a motion in Q1, which would move the end effector up and down. I have a motion in Q3, which would move the end effector left and right? So this would be basically this guy here. Would do the left and right motion. And then I have sort of my joint Q2 here, which combines two things, right? It does sort of a motion in this direction together with a rotation, right? And in this configuration, we would maintain the 3 degrees of freedom, right? So right, I can move right and left, I can move up and down, and I can independently rotate. And the Jacobian for this case would basically be 0, 1, 0. It would be 0, 1.5 or 0.2, 1. And then I would have a 1 here and the 0 here, right? So you would also numerically see that this Jacobian has rank 3. And the important difference is that basically here I get up and down from either this one or that one, right? So I basically have 2 joints that do exactly the same thing, move me up and down, whereas this joint Q2 is doing a combination of right and left and rotation. And so I cannot control these 2 things independently. This is, I think it's a good discussion. My main purpose for all of this is to make you think again about what is a Jacobian doing, degrees of freedom, motion spaces, because we will use these Jacobians throughout the rest of the class. And as I now move into our next chapter, which is now on multi-body dynamics, I want to introduce something that is actually called the Jacobi transpose mapping. And I brought a version of the robot that we just saw, but now I want to start reasoning about forces. And despite the fact that it's a really silly robot, I want to think about this robot as a controls engineer. Right? I want to control this robot. I want to make it move. I want to apply torques to make it move. And the first thing that you would do when someone comes to you and say, hey, here's a robot, can you control it, is what would be called gravity compensation. And what I mean with gravity compensation is that if my robot is holding a very heavy object, very, very heavy cell phone here, and I would turn off all the motors, it would just collapse. So before I even start thinking about moving the cell phone around, it would be nice to compensate that effect of gravity to say, apply motor torques. In my case, this is predominantly a shoulder torque, moving up here to balance the gravitational force acting here on the load. And of course on the other links as well, but let's assume my arm is light compared to the cell phone. Right? And this is something that's configuration dependent. If my arm is fully extended, I need to apply a large torque because I have a long lever arm between my joint here and the object that is creating the torque. If I move the arm in, right, now I made that lever arm very small, and my shoulder has to apply a much smaller torque. Right? So the whole thing is configuration dependent, and again, you see, is somehow dependent on lever arms. And I want to do this here with this simple example again of my little robot. I have my two joints, Q1 and Q2. Dimensions are given. I have sort of my inertial frame of reference, and then I have again these definitions of what I call X, right? Here in the 2D case, positions and orientations just put together in a tuple. Later, of course, these would be orientation transformation matrices and 3D vectors. But for simplicity, I introduce everything here in a plane, right? And I can take these coordinates and put them together into what I call X, right? It's always me who defines what is X. In this case, I care about the positions of both of these bodies, so I put everything into this vector X. I have my vector of generalized coordinates with my two joints Q1 and Q2. And if I would look at explicit constraint function, I can compute X as a function of Q and then take the derivative to get my Jacobian here. Here I want to do a bit of a shortcut. Who can tell me what is the Jacobian JF? Just by looking at the problem and recalling what we just discussed. What should be the first column of the Jacobian? So this will be Q1 dot, right? And what should be the elements, right? What should I put into this first column of the Jacobian? 0, 1, 0.
0, 0.
And then you say 0, 0.
0, 1, 0 again.
Exactly, right? So both mass 1 and mass 2, if I apply a velocity to joint 1, are going to move in a purely vertical direction. So I get a motion in y1 and a motion in y2. What are the first three elements here?
0, 0.
These are all zeros because joint 2 is after body 1, right? After, in the sense, we're going from root of the tree to the leaves. And then the most difficult one, what is going into these last three elements?
L times the sine from minus 45 degrees and the cosine.
Okay, so those are going to be the same, right? Sine of 45 degrees is square root 1/2. Cosine is square root 1/2. There's here's a negative, and then what do I put in the last element?
1.
1, right? So these are now the lever arms measured from here to here and from here to sort of that line. Here's the 1 because this will introduce a rotation which is going to reflect it with gamma 2. So those are the kinematics. But now this robot is hanging out on this planet, on Earth. And on Earth, we have gravity. So these masses will both experience forces that are pulling them down, right? And in this inertial frame of reference, my Fg, my gravitational force of body 1, is simply going to point in the negative y direction. So I have no force in the y direction. I have minus m1 times g in the y direction. Sorry, 0 in the x direction, minus m1 times g in the y direction, and 0 in the z direction. And then here I would think about Fg2, the gravitational force acting on body 2, which is very similar, just that I have minus m2 times g. This would be now in a 3D Cartesian world. If I think about this more in this space X, right, where we combine things to the 6-dimensional vector, where every third element corresponds to a rotation, I could also represent this force Fg, right? The first element would be the force in X acting on body 1. The second element would be the force in Y acting on body 1. The third element would be the torque about gamma 1, right? The rotational torque acting on this body 1, which is 0 in this case. And then I do the same for body 2, so no force in x direction, minus m2 times g in y direction, and again, no torque. So that's kind of important that I'm mixing here forces and torques, right? This is a torque, this is a torque, the others are forces. I could think of, if I think about gravity, it's always going to have that structure, but I could write this whole thing much more general, right? So if I think about this basically being the rotational joint, gravity is pointing in this direction, but maybe someone opens the door and opens the window, and there is airflow coming through here, which is pushing against my center of gravity of this body. But because it's an airflow, it's actually not acting at the center of gravity, but acting on my arm overall, so it's not only creating a force, but also a torque, right? And in that case, I would then have really a fully 6-dimensional vector of basically external forces, right? And if we do this in 3 dimensions, this thing would have 12 dimensions, because each of the 2 bodies that we're looking at, body 1, body 2, would get a 3-dimensional force and a potentially 3-dimensional torque. So very, very general idea. And now I want to control my robot such that it's not moving. And to do that, I can apply torques at the joints, right? So assume someone put a motor there, a linear actuator, maybe a ball screw, at joint 1, which produces a torque of tau 1, generalized torque of tau 1, and joint 2, we have an electric motor producing a generalized torque of tau 2. You have a question?
Yeah, is the vector Fg, is that the vector of generalized forces, or is it just Fg1 and Fg2 stacked?
It's something in between. It's sort of in this X space. Right? So it's combining translation, so forces and torques. So of course I not only stack these, I should have written this, maybe I write this differently, pardon me. I should write these here as two-dimensional quantities. And then I would have, in this I system, right, I would have a torque mg, which is just going to be 0. Maybe that makes it clearer. Right, because we're living in a two-dimensional world.
Why are the torques 0?
Because gravity is not producing any torque about the z-axis.
But for the second mass?
Also not, right? It's not producing a torque about the z-axis because the force is acting directly at the center of gravity. So I'm not going to get a torque about the center of gravity.
So we always use the center of gravity as the point of reference?
For this particular case, yeah.
Okay.
All right, thanks. I think that was a good clarification, right? And then the answer is here we just stack everything on top of each other and combine it into something 6-dimensional. So we have basically here our forces in Cartesian X space, and we have our motors. And my task now is to balance these Cartesian forces. So balance the gravitational forces that are acting on the robot, forces and torques, but the torques are 0. So that means I somehow have to create a balancing set of forces and torques minus Fg. And I have to do this with joint torques, generalized torques, right? Because on joint 1 we have a linear actuator, joint torques tau. And there's one actuator, linear actuator at joint 1, and a rotational actuator is a traditional motor on joint 2. Okay, that's what we want to do. And now comes a philosophical question. How is that possible? Right? Our F vector is 6-dimensional, and we have 2 motors. Why does that work? Right? It obviously works because, I mean, I'm describing a simpler version of my arm, and I can hold my arm steady.
We have a Jacobian.
Do you want to go first, or? Okay, then go ahead.
We have a Jacobian that transforms 2 motors in 6 degrees of freedom.
Okay, I'm not sure if that answers my question, but it describes it in a more formal way, right? I have a Jacobian that goes from a two-dimensional generalized coordinate space to a 6-dimensional Cartesian space, right? And now I'm trying to go back, and if I just do a counting argument, I have 2 motors to balance 6 forces. It seems like I'm screwed, right? So, Luca.
We only have 2 degrees of freedom, so we only need 2 motors to restrict it to 3 of 3.
Right, so it seems like if you count it that way, you just have to block the 2 motors and the thing shouldn't move. But where's the other 4 forces coming from? I don't know, maybe you were first.
And probably because the lever arm of that's connected to the motor is just the possibility to move and rotate and get the forces in all directions.
So you think I could rearrange my directions of motion? But that wouldn't solve it fundamentally, because at any point in time, I would just have 2 directions, right? So for me, this would move. I could not hold my arm like this. I would basically have to do something like that and then balance it, and I could do that. But I obviously can hold my arm still in any orientation.
So I was thinking maybe because of the constraint forces.
Yeah. So there's something missing in all these equations, and this is the fact that we have constrained forces. So if I just think about my arm as having a rotational degree of freedom in this direction, right? If I get a gravitational force pushing down, I have to use my biceps to push against it, right? So this is actually exhausting for me. if I get a force in this direction, right, and let's assume my shoulder is fixed, right, trying to push that way, my biceps doesn't have to do anything because those forces will go purely into the constraint forces, right? So the ligaments in my body, the ligaments are providing these forces. If I think about the door, right, as again a constrained system, you can pull on the door as much as you want. As long as you're not creating a torque, it's not gonna move the door, and all you're gonna eventually do is you're gonna break the hinges. Right? If you push too hard here, you're also going to break my joint. Right? This is what skiers do when they break their ACL in their knee. Right? That's exactly what happens. It's not a muscle injury because the muscle does only this motion, but you obviously got a rotation about some different degree of freedom, which went into the constraints provided by this ACL, this anterior cruciate ligament. And if that force gets too large, then the ACL will rip apart. So again, this question of what does a joint do, right? Where do we want to focus on? And in all these things that we're going to do, we have to keep in mind there's additional forces happening that we don't see because they're constrained forces, and we only care about what the motors are doing, which is a controls perspective, right? If you're the mechanical engineer who has to dimension the bearings for this robot, you would have to take a completely different perspective on the problem. Good. How large should my motor torques be? So how large should I set tau 1? And without doing any fancy math yet, just by looking at the problem, how large does the force be at the motor?
G times M1 plus M6.
Yeah. So I basically have to push both masses upwards against gravity. So tau 1 is m1g plus m2g. How large does tau 2 need to be? Does tau 2 depend on m1? No, right? That's in a sense closer to the root, right? So tau 2 only has to balance m2, where I now have to reason again about this lever arm.
L times sinus of minus 45 degrees, which means square root of 4.5 times L times m2 times g.
Times m2 times g. So we see here that somehow lever arms again play a role, right? So here it's very clear we have a lever arm. Sorry, not that thing, but this thing here. And here we don't see a lever arm, but that is because we have a translational motion, and the translation is basically giving you a transmission ratio of 1, right? Tau 1 is acting in the y direction, gravity is acting in the y direction. And this looks close to what we have here, right? Somehow this is related to the Jacobian. And I can show you immediately that it has to be this way by looking at power. If I think about a little robot, and if I think about the power that I put into the robot and the power that I take out of the robot, those two have to be equal. So the power in the joints given by motor torques times motor velocity, and the power that I do in the Cartesian world given by velocities of my centers of gravities multiplied with the forces acting on them, those have to be the same. So power in joints is going to be the dot product between motor velocity and motor torques. And in this Cartesian world that we set up, it would have to be the dot product between these Cartesian velocities, which is now this combination of 6 translational and rotational velocities, multiplied with the force that we want to create, which is minus F times G. I can now go ahead and write that as this dot product, right? This dot product of dual spaces. In general, we talked about, right, there's no dot product with Q with itself, right? Because we wouldn't even know what the units are, but we can define sort of this dot product between dual spaces, between velocities and torques. And in terms of numbers, we would simply write this as Q dot transposed times our motor torques T. And we can, of course, do the same in the Cartesian world. So that's going to be X dot transposed times minus Fg. And now I can use my Jacobian to compute X dot, because X dot is my Jacobian JF times Q dot. That whole thing gets a transposed, is multiplied with minus Fg. And then if I pull out the transpose, I get Q dot transposed times JF transposed times minus Fg. And now I can just compare. Over here, I have my motor torques. And over here, I have JF transposed times minus Fg. And those two have to be the same, because if I multiply both with Q dot, an arbitrary Q dot transpose, right, I would always get the same power. And this leads to what I call the Jacobi transposed mapping, where I say that generalized torques, tau, and I change my color scheme a little bit here, because I want to, again, go into this distinction between generalized coordinates. So that's where tau lives. That's where my Q and Q dot live. And Cartesian world, this is where my forces F live. This is where my X and X dot would live. And tau is simply JF transpose, the transpose of the Jacobian multiplied with F. And this is based on the same Jacobian that would give me the velocities of X dot from Q dot. So very, very simple equation, very, very powerful. If you think about it, maybe not too surprising, because the Jacobian is handling lever arms. And if you have a lever, right, it will amplify your velocity one way, and it will amplify your forces the other way. Or any transmission that you have, right, amplifies velocity in one direction, amplifies torques in the other direction. Is that what we see, right? JF goes from Q to X. JF transpose goes the other way, right? From F from green to tau to red. Questions? Let's do this with a quick example, right? The example that we have here. So where do I start? So my torques tau, I know they're going, in this particular case, they're going the transpose of the Jacobian with this force minus Fg that I would like to create. So I need the transpose of the Jacobian, which I can just copy from above. I have here my lever arms, minus L 1 over 2 plus L square root 1 over 2 And here I had a 1, and then just to match this in the top row, sorry, there's a 1. That now gets multiplied with minus fg, so 0 m1 times g, 0, 0, m2 times g, 0. Multiply everything together. I will end up in my top row with m1g plus m2g, and in the bottom row with L 1 over 2 m2g. So what we expected, and we see here these lever arms at work, and what you would also see is if we had other directions here, if we had a force in x, right, maybe an aerodynamic force acting on our robot, or someone has, I don't know, a really strong magnet in the lab next door, and there's magnetic forces acting on the robot, you would get additional entries here, which would then go through the other lever arms. And it's a projection, right? We end up with the torques that live in our generalized constraints, in our generalized coordinates, and then the constraints are gone. And you could imagine, we're not going to do this here, but if I would use JG, the constraint Jacobian, I would then project in exactly the other space, right? Here I'm projecting into the motion space. With JG, I would be projecting into the constraint space, which would tell me when my ACL would rupture. In general, this is something what Gonzalez said before, right? We have Jacobians that are not square, right? My my choice of Cartesian coordinates here was 6-dimensional because I have two bodies living in a planar world, and the way I built my robot, my torques were just 2-dimensional. So the Jacobian is going to be a 6x2 matrix, which immediately means that we cannot invert it. So I'm kind of stuck with these directions, right? I can go from Q to X, and I can go from F to tau, but I cannot go in the other direction because I cannot invert this Jacobian. In this particular case, I would call this a tall Jacobian or a skinny Jacobian, right? Because it's taller than wide. Here it's 6 tall and 2 wide, so a tall Jacobian. For tall Jacobians, we essentially have the issue that we have fewer degrees of freedom in Cartesian coordinates, in generalized coordinates than we have in Cartesian coordinates. And the simplest version of that is a really stupid robot where I have just one joint, but I have an end effector that is moving in the plane. I could even claim that this end effector is moving in 3D space, right? And depending on how I look at this, the Jacobian is either 6x1 or 3x1. Going from Q1 to my Cartesian velocities is simple, right? Because from Q1, I could simply deduce if I apply some Q1, the system is going to move in this direction with a velocity of x. If I try to invert the Jacobian, I would basically be telling my robot, I give you an arbitrary 3 or 6-dimensional velocity. Please give me the corresponding joint velocity, which for such a robot is actually a really mean thing to do, to tell it to, hey, could you move please that way? Right? What are the motor velocities that you need to go in this direction? And your robot is just helpless. Yeah, sorry, can't do it. Yeah. So that's sort of physically why you cannot invert it. If I think about it the other way, right? If I apply a Cartesian force, right? And this could also now include a a torque component. But it would be fairly simple to immediately say, oh, if there's a force coming in like this, right, here's my lever arm. I need a particular torque tau1 to balance this force. But there's also constraint forces acting, which basically have to balance F here at the base, right? So the bearings of this little robot have to take a big chunk of F. And then if I were to change my force F to actually right through the joint, you would immediately see, right, the joint would not need to produce any torques, but the bearings would see all of F, right? And then if I turn this around, right, I'm very mean to my robot, and I pull really, really hard that way, I might be able to get it to move that way, but on cost of breaking the bearings. So this would be the tall Jacobian. And then there's sort of the opposite version, which is called the fat Jacobian, where you have more degrees of freedom than you have, or more joints than you have degrees of freedom in the Cartesian space. So you have 1, 2, 3, 4, 5, 6, 7 joints, right? All with some Q1 dot and all the way to Q7. But if this is a 3-dimensional robot, it can still only move in 3 directions. And going from Q to X is simple. Once I know how fast all my joints are moving, I can figure out in which direction X is going. Now, if I try to play the same game that I had before and tell my robot to move in some direction X and ask it what are the corresponding joint velocities, it's not that it's not able to do it, but it's an ill-defined problem because the robot would have infinitely many ways of creating this motion, right? It can basically do internal motion characterized by the null space of the Jacobian. If I think about forces, again, if I apply a force to my end effector, and I'm curious about what the individual joint torques have to be, right? I just have to think about the line of action of that force and look at the lever arm that each joint has with this line of action, and that would basically give me the torque required at each individual joint, right? In this direction, the problem is well defined. Going from F to tau, I can figure it out. What about the other way, right? Someone gives you 7 taus and asks you what is the force F that balances that tau. Right here, we'll be thinking about balancing forces. I give you force F and you give me the torques that balance F, and that problem is well defined. If you give me 7 taus and ask me to balance those 7 torques with the force F, what is going to happen? I'm screwed, yeah? Maybe I can balance the forces to keep that point here stationary, but all the other torques are going to create an internal motion, right? So when I basically say balance the forces is I apply force from the outside to make sure that the robot is not moving. And if I have arbitrary 7 joint torques, whatever I do with my 3-dimensional force torque vector coming from the outside, I'm always going to end up with some internal motion. So that's why, for the case of a fat Jacobian, this direction is not working. There's the exception, right? Sometimes you have a robot. This is what I would call well-designed, that has 3 degrees of freedom to move in 3 dimensions. And then the Jacobian would be invertible, but even there I would be very careful because you could run into these kinematic singularities that we saw here. Right? Here I have, basically, if I look at this point P2, I had just that one, right? That was a 3x3 Jacobian, right? That in this situation can be inverted because it has a rank of 3. In this situation cannot be inverted because it has a rank of 2. Right? So I've seen books where they invert Jacobians sort of as first order of business. Let's invert the Jacobian. It's like never attempt. Works sometimes, and even then it's not enough to do a counting argument, but then you would really have to check for singularities along the way. Good. Jacobi transpose mapping, check. Question.
Can you again explain your comment on the meaning of JG transposed times F?
So these are the directions in which I can move. And JG, sorry, I might have to do the math myself first, but JG would sort of be the orthogonal space, the directions in which you cannot move, right? Describing basically the constraints. And so that would then project these external forces. I'm basically separating into two things, right? I'm separating them into the space in which I can move, right? So this would be the muscle injury, and the space in which I cannot move, and that would be the joint injury. I'm just not, at this point, not 100% sure about the map, whether it's JG or JG transposed. Yeah. And it also may be that it's going the other way in terms of you going from constrained forces to JF. I would have to look into it. Okay? Good. Mean question. No, good question. Thank you. Any other questions? They can be mean. They can be meaningless. They can be... No? Then, finally, here we go. Dynamics. All this build up. Now we want to talk about multi-body dynamics. And I will do what I will do in the next 20 minutes, actually 3 times. So I will do this fairly fast. I want to first talk about a simple particle, constrained particle, then about systems of particles, and then about systems of rigid bodies. And the reason why I want to build it up is because in addition to introducing the math, I would also want to make sure that you get a little bit of a physical understanding, which is easy for one particle, is already challenging for 2 particles because it has basically a 4-dimensional Cartesian space in which it can move, right? One particle can do x and y. 2 particles are moving in 4D, so I cannot even visualize that anymore. And then if you think about 2 rigid bodies, you're immediately looking at 12 degrees of freedom, so no way I'm gonna visualize this. When we talk about dynamics, right, my goal is now to relate forces and accelerations. And the basic idea is to use this Jacobi transposed mapping that we have just seen. But maybe let's dive in with an example. Simple pendulum. Here I have a mass sitting on this link, which constrains the mass to move around this joint here, rotational joint with joint angle Q. And in general, right, knowing Q, I can compute the position of this pendulum. I could go ahead and compute the velocity of this pendulum. So this would be x dot, or v as we called it. And I could go ahead and compute the acceleration. In which direction should the acceleration point? And if I draw in x double dot, where should I draw it? We don't know, right? This is kind of the whole point. We want to figure that out. What is the acceleration? It's going to have 2 components, right? I have, if this were sitting, floating in space without gravity, and I would have a uniform velocity about q1, right? This would just keep spinning forever. And I would get an acceleration component along the constraint. But since I have gravity, I know that this pendulum is basically going back and forth, so there must be some acceleration sort of tangential to the arc that it's moving on. And in this case, we would probably get both. So maybe something like this is the acceleration x double dot of our little particle. And it's being accelerated because there is an external force acting on it, which is our gravitational force Fg, and there is a constraint force acting on it, which I would call Fc, right? And since this is a point mass on a rod, that constraint force has to be in the direction of the rod. And now for the single particle, I can go ahead and write down my equations of motion for a particle. Mass times acceleration equals sum of all forces, which in this case is Fg plus Fc, our constraint force. And we immediately see the problem because we would love to compute x double dot, but we can't do it because we also don't know what Fc is. So we don't have enough equations here for our unknowns, right? In this 2D particle world, we have two unknown accelerations, two unknown components in Fc, and we have only a two-dimensional vector equation. This is basically Newton, right? Newton's third law. And I want to rearrange that a little bit and interpret it slightly differently. I'll just throw everything on one side. So Fc plus Fg plus minus m times x double dot is going to be equal to 0. Same equation, but it's now a little bit nicer to see that we basically have a balance of forces, right? So this is a force equation. Vector valued, right? Two-dimensional for a little particle. And I'm basically going ahead and interpret this term minus m times x double dot. I interpret this as a force. We're going to call this the D'Alembert force. So this is the guy, Jean D'Alembert. He was born, what was it, 1717. So Newton published the Principia Mathematica in 1687. He was born 30 years later. Probably didn't invent this right away. So we're looking at about 50 years of people looking at this until they realize I can interpret this as a force. And I could draw that here, right? It's a scaled version of x double dot. So this would be my D'Alembert force minus x double dot times m. And this is equal to minus p dot, of course, right? Change in linear momentum. And what I see now is that I'm looking at the force balance, right? Where Fc, Fg, and this D'Alembert force, they have to form a closed vector chain, sum up to 0. What I will do with this equation is that I will go ahead and pre-multiply it in the sense of a dot product with a velocity, a so-called virtual velocity that we write as delta v. And that gets multiplied with the entire expression, so Fc plus Fg plus my D'Alembert force minus m times x double dot. And since I have a force of 0 here in the brackets multiplied in the dot product with the velocity, I get 0, and that 0 is a power, right? The product of velocity and force is, of course, power. So I have now a power equation, which is a scalar equation. Now, what is this velocity that I use to pre-multiply? This is a virtual velocity. And virtual means I freeze the system in time. And then I move it virtually consistent with the constraints. And what that basically means is I disable any rheonomic constraint. So if I think about a slightly different example where I have this hydraulic cylinder here that we've already seen at some point with a mass on top. So this is a rheonomic version of the example that I introduced. So this is not the nicest hydraulic cylinder. Right? So the difference now is I have a rheonomic constraint where my L is a function of t and L dot is not equal to 0. So this thing is moving maybe in this direction. What that means is that I'm not moving on an arc anymore, but I'm moving in a spiral, right? So I'm rotating and I'm at the same time moving towards the center. So my actual velocity is going to look something like this. Whereas the virtual velocity would disregard the contribution of the rheonomic constraints. That's what I mean would freeze the system in time, right? So I will not say my constraint is changing. I would simply set L dot equals 0 or disregard L dot. And I would get my delta V, my virtual velocity, still sort of orthogonal to my rod or to my hydraulic cylinder. And this is the important notion here, right? My delta V in some inertial coordinate system can be written as my Jacobian JF simply multiplied with Q dot, where I call this now a virtual Q dot. So this is not really the velocity I have, but any arbitrary delta Q dot, any velocity that I could put on the joints could give me some velocity. And the difference to the equation up here is that I disregard this term from the rheonomic constraint, right? So delta FC delta T does not contribute. That's what I mean with virtual velocity. I only move my joints. Doesn't have to be the real velocity. Could be any velocity I can think of within my joints. And the rheonomic constraints do not contribute. And the virtual velocity has an interesting property because the virtual velocity is always going to be orthogonal to the directions of the constraints. So the product of virtual velocity with constraint forces is going to be 0. Right? Virtual velocity is basically the span of my Jacobian. My constraint forces live in the span of JG, of the constraint Jacobian. Right? And since these two are orthogonal, the product between FC and virtual velocity is always going to be 0. Right? It's not the same for rheonomic constraints. Rheonomic constraints can produce power, but scleronomic constraints do not produce power. Right? They're purely passive. They cannot produce power. Good. Where do we go with this? Well, I substitute now my delta Q dot, which I have to write in a transpose here. My delta V with JF times delta Q dot with the transpose here. Nobody moves? What do you think? It's going to turn for 9 minutes? No. And then here I still have my constraint forces. Now I express everything in coordinates, right? Since I write this dot product now in coordinates. So we have Fg in coordinates, and we have our D'Alembert force minus x double dot in also in I coordinates, and of course this is still 0. And still an equation in units of power, units of virtual power. And I now break this up into the product of my constraint forces with this expression and the product of the other forces, and the other forces being sort of the active forces, gravitational force, plus the D'Alembert force. Now it's still 0. And now comes the part that we discussed before, where I say that this here has to be equal to 0. Because this is virtual power, which is produced by these constrained forces, while we only allow motions that are consistent with the constraints. And since the constraints are purely passive, right, there's no motors, we're just talking about joints, and we're talking about joints that are frozen in time, right, purely scleronomic joints, they cannot produce any power. So what we see here is that this will be 0 since the virtual power, and this is important, right? An actual joint may have a rheonomic component, but here we're talking about the virtual constraint, creating this virtual velocity. Since that is passive, it creates no power. And the way we thought about this in the past was basically that the directions in which we can move, right? This delta V is basically the span of my Jacobian JF. That is orthogonal to my constraint forces Fc, which are spanning the constraint Jacobian JG, right? The implicit constraint Jacobian JG. And those two are always orthogonal to each other. That's another way of thinking about this. Which means in our little equation, we are just left with the terms on the right-hand side. So Q dot times JF transpose, is still missing a transpose, Q dot transpose, times our gravitational forces and our D'Alembert forces. And this is great because we just got rid of one unknown, right? We didn't know what these constraint forces Fc are, but they don't show up anymore. And I'm only left with my unknown accelerations. Furthermore, I never really specified what these virtual generalized velocities are. So the equation that I have here, that must hold for all choices of delta Q dot that I can pick. And that means that whatever we have in the second part of the equation has to be equal to 0. So JF transpose times my external forces plus the D'Alembert force is going to be equal to 0. And now again a 0 with a vector on top, because we're now talking about generalized torques or generalized forces. Basically in this tau space, in this motor torque space, because what we're doing here is a Jacobi transpose mapping, right? I take Cartesian forces, Fg is a Cartesian force, the D'Alembert force is a Cartesian force, and I multiply it with the Jacobi transpose to project everything into our generalized coordinates. So exactly what we did at the beginning of the class, right? This is nothing else than this Jacobi transpose mapping that we had here, where F are now my gravitational forces plus the D'Alembert forces. So I just look at the acceleration times mass as a force, multiply this in the Jacobi transpose mapping, and get my torques. And since in our simple example we didn't have a motor, on the right-hand side we're bound to get a 0. So here we have our Jacobian that projects from forces F, Cartesian forces F, to generalized torques tau. And then I will do one last thing. Because I want to substitute my acceleration, and I can do this using the same Jacobian JF. I use my Q double dot, plus I have my bias acceleration, which now could also include accelerations coming from a rheonomic joint. And then if I rearrange and put this all together, I will get JF transpose times M, so I'm flipping the sign, times JF times Q double dot plus JF times M, sorry, JF transpose times M times my bias acceleration sigma minus JF transpose times my external gravitational forces is going to be equal to 0. And now we have a direct relationship between our joint accelerations, the external forces, and the bias accelerations. And when we do forward dynamics, we know velocities and positions, so we can compute sigma. We know this. Everything is known. The Jacobians, they depend on Q. They're known. And I could go ahead and solve this equation for Q double dot. If I want to do forward dynamics, if I want to do inverse dynamics, there's a little thing missing here because we don't have a motor in our example. This is called the projected Newton-Euler equation. This is actually only a projected Newton equation because we just thought about linear accelerations. But if you think about this, what did we do, right? We took Newton's equation, this one here, and simply pre-multiplied it with JF transpose. So we did a Jacobi transpose mapping on the entire equation, which we can still see here, which took the entire equation, converted it from Cartesian into generalized coordinates, and in the process got rid of all the constraint forces. Because we said early on, right, in this Jacobi transpose mapping, I take an external force and break it into two components. One component's covered by the constraint forces, Fc, and one component covered by the motors, tau. And after the projection, right, after applying JF transpose, we only see the motor torques tau. The contribution of the JF goes away. And if I take JF to begin with, run it through this projection, it's just going to vanish. And then the only second thing that we did is that we sort of went the other way around, where we went from generalized accelerations to Cartesian accelerations. And this is what we will see again in the next couple of lectures. I go from Cartesian accelerations with JF, with the appropriate lever arms, from generalized acceleration with JF into Cartesian world. In the Cartesian world, I multiply with m to get a Cartesian force. And that force I project back into my generalized coordinates. So it's very simple. We're just changing coordinates 2 times. And that allows us to write then everything in this very compact form. This is based on the principle of virtual power. It's called Jordan's principle of virtual power. In the US, this is also called Keynes' method, where Keynes' idea is basically to write these virtual velocities as these partial velocities through the Jacobian. We will see all of this again on Thursday. Yeah, have a good week. See you then.